continue with our lecture series on sorting algorithms and sort of our beginning introduction to algorithms in general. So hopefully everyone was able to get to part one of the project completed. So that was where we covered most kind of common iterative sort algorithms. But now, and as we've noticed, most of those algorithms were worst case. How bad were they in the worst case? We're talking about bubble sort, insertion sort, selection sort. They were all pretty much the same worst case. What worst case were they? Yeah, Layla's got it. They were all worst case n squared, which it's not the worst, certainly, but it's also not great. So now we're going to have to try and see if we can improve on our algorithms. And we're now going to start to take a look at recursion as a potential solution for sorting, and see if there's something that we could do with recursion to improve our performance. So real quick, can anyone tell me what recursion is? I guess it's that GIF that Joshua linked. Yeah, so when a function uses itself, right? Does anyone know, sort of, when we write a recursive algorithm, what are the two parts of a recursive algorithm that we have to make sure we have? Mm-hmm. Yeah, first part is definitely the base case. And what is the second part? Mm-hmm. Kind of the recursive step, or yeah, essentially something that will actually iterate toward the base case, for sure. Great. So, and what is it that we need the base case for? What if we were to miss a base case? What would happen to our recursive algorithms? Mm-hmm. Yeah, we'd go on forever until something screams at us in the computer. Usually, the interpreter or the operating system will say, "Hey, you can't just keep spinning your gears." Sometimes when applications crash and you get that application crashed message, or message application's not responding, very often it might actually just be stuck in some kind of infinite loop and doesn't know how to get out of it because maybe something didn't end up reaching a base case. Happens quite often because recursion is sort of patently pretty tough to debug when issues arise, because unlike iteration, where you can kind of see all of the data right there in your code, you can see sort of in a loop what step you're on, and all the local variables and things like that, and all the global variables. With recursion, we could be modifying global variables in each step, and we're not really sure what one step did that might have modified another step. So that's probably the thing that most computer scientists are afraid of most of the time when dealing with recursion. But when we really break down a recursive algorithm into its base case and its step, and we make sure that the step has a way to get to the base case, and we make sure that the base case returns the correct thing, generally recursion ends up looking kind of very nice and actually easier to read quite often. And we'll see an example right now of a much more efficient recursive algorithm than we for sorting than we have used before. And we're actually going to see two versions of it, an iterative and a recursive version, and we'll see that the iterative looks a lot weirder. Cool. So it looks like a lot of you guys understand what a recursive algorithm is. So a recursive function, once again, is anything that will call itself one or more times within the function itself, and it'll sort of keep calling it and calling it and calling it. We need a base case because if we don't ever have a way to stop this loop of calling itself over and over, we'll just keep spinning up new instances of this function until we run out of memory or our computer crashes or something like that. So before we dive into before we dive into implementing recursion, we also want to make sure that we understand how to analyze the performance of a recursive function. So analyzing recursion is a little bit trickier than analyzing iteration because it's not quite as intuitive at first. But taking a look at something like this very simple recursive function. So all this does is basically iterate through n until n is 0, and then it will return out of the function and no longer keep calling these n's. Let me open this up real quick. Does anyone already have an intuition for what the runtime of this function would be if we were to call an instance of ndemo? I apologize. I think my internet just cut out. I was saying that Layla was correct that it is n. It is O of n. So how come this function is O of n? Seemingly nothing in the function itself will run n times. So how we analyzed before with iteration, we'd look at each line, but this line runs O of 1. Whoops. This line runs O of 1 times. And I mean, technically calling a function is also O of 1, right? But in total, as we can see, we are going to end up calling this line n times. And so it might not necessarily be super obvious where it is that, or how it is that we have to call this n times. We have to essentially look at what's going on inside of the function call. So here we're doing n minus 1. So, and we have to look at the code itself and see what the base case is and kind of see what the relationship between sort of what is our stepping function, which is n minus 1, and what is our base case. And we can kind of infer from this that we're going to go, if n was 10, we would go from 10, 9, 8, 7, and so forth. And that will result in n calls of this function until we actually end. And so that will give us our O of n. Now here is a little bit harder of a function. This time we call toNdemo twice. So what will be the performance of this function? Anyone take a guess?
I'll be right back. I'm in class.
Okay. So I'm seeing some options for n, some options for 2n. Any other guesses? So the actual answer is it's actually much, much, much worse than 2n. This is actually going to be 2 to the n. Because this is no longer linear. If you think about it, each call calls the function 2 more times. So when we examine how a recursive function sort of expands and propagates, every time a function gets called, let's say we kind of draw a little circle for the function being called. This might be a process, some kind of step. This alone might be, you know, an O of n step. Maybe the function does some O of n operations. But either way, let's just say this circle right now, we call the function once. If it calls itself twice, and in here it does O of 1 step things. When it calls itself twice, what happens is we create 2 more instances of this function. So 2 more calls already, right? So at level 1, we kind of have 1 call. Level 2, we have 2. And what's going to happen is until all of n is done, we're going to keep doubling how many calls we're going to have. So in this case, we now have 4 calls. So we actually, in total, with n equals 3, we've already called 1 plus 2 plus 4 times. We've already called 7 times, or I guess 8. So 2 to the 3 will be 8. The upper bound is 8 in this case. So as we can see, and if we keep going, again, we'll reach 8 down here, and as you can see, we'll reach 16. So this is not a linear expansion, right? This is going to go to 16 and 32. This right here is an exponential increase in how many calls we're going to make at each kind of level. So if n was 5, then we would end up making 32 calls, or I guess what, 63 calls, because I have to get a calculator for this. I don't even, what's 2 to the 5? Does anyone have that knowledge? Yeah, it's 32. Wait, is it? 1, 2, 1, 0, 1, 2, 3, 4, 5. Yeah. So we're actually going to end up with 32 calls in total. So as we can see, just by adding 1 more line, we went from linear to exponential because of this whole thing. Even that all we have is just 1 operation in here, we still end up calling this line a total of 32 times. This is kind of the trickiest part about recursion, is there isn't so much as it sort of just calls the next step. It's not kind of like a iterative process of this step is completely done and this one is moving on. In fact, none of these calls of this function are actually done until we reach a final return that sort of kind of kills this one and ends up killing this one and ends up killing this one, ends up finishing this one. So in fact, this function, if it were to be stored in memory, or if we have variables stored in memory here, they don't leave memory until the final return. All of this sort of expands outward in an exponential way until we hit the base case and all of these get terminated. So, and what would be the runtime if what would be the runtime if I add 1 more here? Yeah, it would be 3 to the n. So when we're looking at recursion, we have to look at how many times we call the function, and then sort of what the relationship is between the stepper and the base case. So in this case, it will take us n times per kind of session to reach our base case. So we have to use that as our exponent. And then how many times we call that function, that is what the base number would be. So this is 3 to the n. So it's not just 3 times worse. It's like, it's a whole other order kind of worse, basically, just adding in one more line. Because now we're expanding to 3 at once, and then we're going to end up with 3 more again and again and again. So this would be 3 to the n. Cool. So with that, you might even think, well, why would I want to use recursion in that case? Sometimes, you're right, sometimes recursion might end up being a terrible option. And we will discuss some good and bad use cases of recursion later. Yeah, it's kind of like the Hydra. You cut one head off and 2 more show up. But there is definitely very good use cases for recursion as well. Because if we take a look at this now, divide n demo. So here we're actually dividing every time we call the function. So what would be the order of this function?
Should be log n.
Yeah. So it would be O of log of n, because every time we divide the current amount by a smaller by 2. So it's kind of like we might start at 8, and then the next time so let's say n is 8. By the time, how many times are we even going to evaluate n or even run this if n is 8? Yeah, I think 3, right? So 8 divided by 2, we'll get to 4. Then we'll divide that by 2. We'll get to 2. We'll divide that by 2. And we'll get 1, and it will be done. So it will be essentially just 3 times that we will run divide and demo, because every time we are halving it. So this isn't a linear relationship anymore. It's basically the inverse of that exponential relationship that we had before, where it's going to be the log of 8. I believe log 8 will be something like 3, right? Something similar to that. I have my phone calculator that I've barely ever used. Yeah, if we look at like log base 2, see if this works. No, I was hoping Google would. Yeah, it's exactly 3. So we're going to run it exactly 3 times. Cool. Do we all understand how it is that we kind of got to this log n evaluation here? Oh yeah, I could also just Google log 8. I was worried that it wouldn't be base 2. It might be the natural log if I do log 8. That's why I didn't want to do that. Cool. What would be the case if I did this? We're going off script for now. We're all going to think about this one. What would happen if I now have 2 calls? It'll probably be like, let's see, if each of these things is log n, right? Then I think this is probably going to end up being 2 to the log n, because if you think about it, each time we are going to let's say n equals 8. I actually want to double check this for myself as well. So n equals 8. We're going to create 2 instances where now we're looking at 4. So we started at 8, we're looking at 4. Then we're going to look at 2 and 2. Still not going to be great. 2 and 2. And I've given myself no space to do the rest. And then we'll do one more row. So we'll have 1, 2, we'll have 4, and we'll have 8 calls. So I guess technically, I think this ends up being linear, because if I'm not mistaken, if my math isn't wrong, I think 2 to the log n. Does everyone remember what a log is? Log n is the same as base 2. I think it's the same. Does anyone remember their math? Yeah, is it the same as n to the half? I think it is, right? Yeah, I think 2 to the log n, if n is 8, would just equal 8. I think any number 2 to the log n would just be n at the end, because I think this is n to the 1/2. And if it's 2 to the n to the 1/2, yeah, okay. I went off script and I totally forgot my math, but I'm pretty sure, yeah, I'm pretty sure we're just going to end up with a linear function. As you can see how I tried to go through that. Off the top of my head, I can't remember the actual math, but we could literally, since we know it's going to be 2 to the log n, because we're calling log n in this sort of recursive time. If you are not as bad at math as me, you will probably know that this should equal n right away. But yeah, so we could still look at this as math equations and figure out the runtime of this. If you think about it, also kind of makes sense. This ends up, yeah, back to algebra 1, right? Yeah, back to, like, I don't know, my first year education in math. You can clearly see how that paid out. Yeah, unfortunately, some of this will have to end up kind of looking kind of mathy, but it is what it is sometimes. Yeah, I'm pretty sure that's what it is, right, Philip? You're right, exactly. So, like, since we're doing 2 to the log of something, we're basically just canceling out those logs. So we basically just end up with a linear equation. Cool. Now, one more question. We looked at, so these are pretty good examples of time complexity. So within the actual function, if we had a for loop that ran O of n times, so let's say we had some kind of code, we'll just do some sort of pseudocode. This is O of n. Then this function would have to essentially be n squared, because we're going to call something that runs O of n times n times. So if we had something in there, that, again, ran a certain amount, we still have to take however many times we are calling this and multiply whatever is inside the function by that value. So in here, if this is 2 to the n, that's because everything here is O of 1. If this had an O of n operation in here, oh boy, then let's see. We would call this 2 to the n times. We would call O of n. So we would call, basically, we would have to multiply n times 2 to the n. Because we are calling it 2 to the n times, and we're calling something that runs n times. If that makes sense. So it's kind of like how we had to multiply things within for loops. We can kind of just intuit that if something is going to take a certain amount of times inside the function, we're calling it 2 to the n times. That is just how much that is in total what the complexity is going to be. Cool. Now, we discussed runtime complexity. We also should discuss space, because space does work a little bit different when it comes to a recursive function. What would be the space complexity of n demo? Let me just get rid of this comment. We no longer have this. So remember, we discussed that space, whenever we create a new variable or whenever we add something to memory, if we might have a relationship to our input. So if we were to create n objects, like we're creating an array every single time in an iterative situation, that would be an O of n space. What would be the order for space for n demo?
So one variable is created, so it will be 1.
Mm-hmm. Well, actually, you can even argue that no variables are created, so it's still O of 1. But it isn't O of 1. Because if we remember back to, again, how this propagates, right? This will call basically itself n times, right? So if n equaled 4, this function would return, but only once this is returned does this function return, and then this return, and then this return. But every time we call a function, a instance of it gets placed into memory we basically create like a little O of 1 space spot in memory that is storing this function and where its code is located in memory. We don't really have to think about it with an iterative function, because with an iterative function, that's just O of 1 space, and that ends up sort of being canceled out by anything bigger, right? So we didn't even discuss it yesterday. But every time you call a function, something does get added to memory. Like the reference to that function gets added to memory. So knowing that, what is the true space complexity of calling n demo? Yeah, it's O of n. Because in all reality, we're actually taking up in memory n slots whilst the function keeps running. And for 2n demo, what do you guys think it's going to be? Best guesses. Let's hear them. Yeah, Layla wins this round once again. It is 2 to the n once again, because if we remember again that 1 call will spawn 2 calls, will spawn 4 calls, will spawn 8 calls, and so on and so forth, given n. So n in this case is basically the depth of this recursion tree kind of thing. And these, every time I draw a circle, an instance of a function is called, and an instance of a function is stored somewhere in memory. So every time the function gets called at all, it will at least have to store that much space in memory. So basically, with recursion, it's almost kind of easy. The runtime is going to be basically the space will be at minimum what the runtime is. But if I were to create an array here of size n, doing this is an O of 1 operation, so the runtime will still be 2 of n, but how will the space be affected? Yeah, yeah, Layla wins one more time. Other people have got to start throwing out guesses. Uh, exactly, it'll be n times 2 to the n. So again, we're calling the function 2 to the n times, and we are going to create n objects per call. Yeah, Layla's now in trouble. So Layla's always in trouble now. I always say that every single lecture. She's, um, yeah, exactly. If we create something of size n and we call it 2 to the n times, then we could basically already tell that we're going to end up creating n 2 to the n instances of some kind of memory object. And once again with this, the runtime of this was log of n. So the memory that it'll take will be anyone but Layla. Right, Philip's got it. It'll be log of n. So in this case, I didn't say that whatever's going on here is gonna create anything new. So the space per call is still just gonna be O of 1. So nothing in here is kind of adding doing anything weird to the space, but we're still gonna end up calling the function log n times. So we're still going to have to store log n instances of the function in memory, going back to, again, how recursion propagates. If I were to put in an array in here in the same way, then it would end up being n log n. Right? If I were to do something like that here, then it would end up being n log n. But because all we're doing is just calling and just comparing some variables, the thing that is stored in memory is the reference to the function itself. Every function, when it's called, needs to store a reference of it until it's kind of killed. So we can kind of say that we're basically creating a local variable at any time when we call a function. It's for the compiler to kind of know once the function is returned, or if the function is called again, where should I call it? Basically, it's to do with that, which we can get into more in much later chapters. But essentially, because something must be stored in memory before all of it's resolved, with recursion, it ends up becoming so that every time we call the function again, we have to create a new instance of it. Whereas iteration, we don't have to do that, because all we do is create the one instance of the function at the beginning. We never call it again. So we don't have to worry about the function creating more instances of itself and storing more things in memory based on the input. It's always just going to be constant. Cool. So any questions on space and time complexity of recursive functions?
So in the last question, if we call this function again, then what will be the space complexity?
Divide and demo?
Yes.
In that case, since we've all agreed that this will run O of n times,
Yes.
then the space complexity would as well be O of n. And again, the whole reason for it is we might not really always be thinking about it, but whenever we call a function, we have to essentially instantiate a little block in memory. So an array will take a huge chunk of memory, a function will still take some sort of amount of bytes. So it's essentially the same as creating a var, I guess there's no vars but you get what I mean, var equals 5. This is O of 1, and so is creating this O of 1. But basically, we can say that in this case, it'll be like 2n complexity, because we create one instance for divide and demo, one O of 1 space for var. That's two things, n times. So it's 2 to the n, but we can drop the 2 and it ends up being linear space.
Thank you.
This is a pretty, I would say, important concept to realize about recursion, and it's something that's going to. It's every recursive function will never have a constant memory to it. It just can't, because I mean, unless it only gets called once, and then in that case, it's not really a recursive function, because it has to keep instantiating new instances of itself. Cool. Arpita, does that make sense?
Yes, thank you.
Awesome. Okay, any more questions?
So in terms of like time and memory, like which one to prefer? We should go for more time or more memory in the real-time scenarios, or it depends upon the company?
Oh, very good question. What should we prefer? So, it's a bit of a loaded question, because sometimes if the difference means a runtime of O of n squared, so like let's say you have a function that you can do in run, you could do n squared, and space you could do in constant. Versus something like where you can do the run in linear and also space in linear. I mean, it's basically, if you're looking at really large numbers of n, then it's probably more worth to maybe do this. That really depends, because it depends on what you're going to end up storing. And I mean, if you're storing 100 just characters, that's not really a lot in memory. But if you're doing 100 squared, which is 10,000 versus just 100 runs, then maybe it's clearly that like this scenario is going to be better. But if you're going to be storing like a huge class or something like that, and iterating over an array of a giant class, and that might take loads of memory, and your space is obviously going to be constrained, then maybe it's best to stick with this. In practice, I find that it's probably almost always better to prioritize runtime, especially when it's a drastic difference like n squared versus n, because we're working on pretty modern computers, and we're most likely all going to end up being full stack devs here. We're probably not going to be running out of space on our computers. So I would say that in general, it's probably good to focus on runtime first. That being said, if you found some algorithm where you can go from n squared and you can do like run in n, but your space is going to be 2 to the n, that's probably a big no, right? So it's kind of all relative to how much worse or better your space is going to end up being. Like O to the 1 constant space versus 2 to the n, that is a huge difference, where this might not be nearly as much of a difference. So you're sort of, this is the fun part of us being software engineers and computer scientists. This is the part where we really have to sit down and think, what is our most common use case? Because we can talk about theory of performance all we want, but in the end of the day, we're putting real data into real machines, and we have to think about, do we have enough space, and do we want to deliver a response back in time, back faster, or do we have no space at all? We're working on like a Raspberry Pi, or we're working on some, I don't know even what is space constrained anymore these days. But you know, if we're working on some tiny little microchip that might not have any space, we might be able to say, okay, we'll make it slower, but we'll save on space. I mean, if you ever find anything that is obviously strictly better, if n squared and you can in n and you can still do it in O of one time, obviously that's not even a question. But that's where you want to sometimes prioritize space. Oftentimes, actually, another tip for whiteboarding and engineering interviews in general, when you learn algorithms, it's also pretty good to learn their runtime and space and be able to explain why the runtime is the way it is and why space is the way it is. And very often you might choose one implementation to write in your interview, for example. And then the interviewer might ask you, okay, well, how can we do this in constant space? And, you know, it's very good to know sort of all the different iterations of certain algorithms, and some sorting algorithms and some search algorithms and whatnot have different iterations or different versions that sort of optimize performance over space and vice versa. And you'll get a lot of great bonus points if you can discuss the merits of either. So you can say, oh, I chose this one because it's better at runtime. I know I've taken a hit on space, but I'm imagining that we can afford a little bit of space to get 4 times better performance. So things like that are definitely good to know about your common algorithms. And when you're doing interview prep and things like that, it's definitely great to be aware of these performance factors.
Great.
Great question, Arpita.
Thank you. Great.
Okay, cool. So if we don't have any more questions about this, and if we do, as always, post in the chat. But let's actually get into creating some better search algorithms. So to recap basically what we did last week, we kind of rushed this part a little bit, so I'll take a little bit more time to go over this one more time. But we created a class called Book. And when I say we, pretty much just me created this without anyone knowing. But let's take a look at it one more time. So we have this book. So let's say we're making a product, we're making Amazon or something like that, and we want to be able to provide a website for people to be able to sort by genre. Or maybe any attribute per se, but let's just start with genre for now. We have a class, and this class stores title, author, and genre. And we want to be able to take an array of books and return all of the books sorted from lowest to highest for genre. Genre being like history, mystery, cooking, things like that. I ran out of things to rhyme with history and mystery. We implemented one sort called insertion sort. And if we recall what insertion sort does, is essentially it takes all of the elements in the array. So if we were to take something like an array of 5, 3, 6, 7, 8, we want to order it in ascending order. So 3 is going to have to end up being over here. So we start at the at the second index, so index 1, and we take the number that is at there, and we basically keep comparing it to its previous number in the array and ask, hey, should we make a trade? In this case, 3 is lower than 5, so we move 3 and 5 over. So at the step, we will end up here. 3 will ask nothing. It's at the end of the array, so it knows that it has to be the lowest number, because to get here, it would have had to ask every single other number if it's smaller than it. 5 will then look at 3, realize that it's bigger than 3, so it doesn't need to go there. 6 will do the same with 5, so will 7, and so will 8. Can anyone remind me what is the worst case complexity for insertion sort?
N square.
Yeah, and how come in worst case it's n squared?
Because each element will talk to the other element in the worst case.
Yeah, so we're going to, in the worst case, have every element ask n times whether or not it should move. And anyone know what the worst case input would have to be for insertion sort for us to guarantee an n squared?
A complete reversal of the array.
Yeah, yeah. So exactly, descending order. Yeah, would be something like that. 5, 3. Yeah, exactly. This would be the worst case because now every number will be completely out of place. Anyone know what the best case scenario would be for insertion sort? In the industry, we call that little o. Yeah, yeah. It's the input would have to be already sorted, and yeah, it would be little o of n. I think little o is the right thing. Either way, the best case would be all the numbers already in the right place, so they all just have to go and ask each other should they do anything, and they would immediately get the answer saying no, they're correct where they are, but we still have to go through every number. Anyone know what the best case scenario for any sorting algorithm? Like, what is like? Can any sorting algorithm do better than O of n?
I guess if it doesn't need to be sorted at all.
Yeah, but how would we know if it's not sorted or if it needs to be sorted at all?
That's true. At least it's O of n, just because it has to go through everything one time just to determine that, right?
Exactly. We're pretty much always going to be bound by this O of n best case, unless like quantum computers figure some crazy stuff out. But yeah, it kind of just a little aside. We'll never do better than n, but we could maybe try to do better than n squared. So this one, worst case, is n squared. You guys had to implement bubble sort, which is also worst case n squared. Trying to think if that's technically part of what you're supposed to answer. I'm just telling you the answers now. Yeah, and selection sort is very similar. In the worst case, it'll still have to go ahead and answer at least n squared time, or at worst n squared time. And then I don't know if anyone got to the count sort one. That one is kind of a bit cheeky. That one technically could be O of n, but it's super limited with the kind of input it can handle. That one is kind of fun. Actually, that one isn't even worst case O of n. I don't know how many people got to it, got to count sort, but essentially you would count how many instances of each number are in the array and then recreate the array. So that's an example also potentially of a n space one if you do it that way. You kind of recreate the array with all of the numbers sort of in the right place. But the worst thing is if you have something like 1 and then like 100,000 million, then you have to count every number from 1 to 100,000, when insertion sort being n squared will be way better than count sort. So count sort is, if you guys have tried it or will get to it, keep that in mind that it pretty much is very specific to some certain data sets. Okay,
Yeah,
cool.
should be small for that.
Yeah, sorting 1 and 0, but sorting 1 and 0, I mean, insertion sort will do it perfectly fine as well. So it's almost not even worth writing count sort many of the times. Cool. So now that we've sort of taken a look at most of the common iterative approaches of iterative sort of algorithms where we kind of go step by step, figure out if a number is in the right place. If it's not, we try to figure out where is the right place for it. And typically that algorithm, that's basically the case for almost every algorithm that we've looked at so far. And just those words alone pretty much imply that it's going to be n squared in the worst case. So we have to look for other options for how it is that we could go ahead and sort a list of numbers. And with that, we can take a look at recursion and specifically a different sort of algorithm paradigm called divide and conquer for how it is that we can solve this problem. So I'm just going to open up just a blank canvas for a second. And basically, one thing that recursion is really good at is this concept that I just called divide and conquer. Has anyone heard of divide and conquer, and anyone know what sort of the two steps of dividing and conquering mean?
Well, in the Army, we tried to divide our enemy into two and overwhelm them.
And then conquer them that way, right?
Yeah.
See, it's basically very similar. I mean, I'm assuming in the Army, there could have been logistical reasons why you wouldn't want to approach a whole force head-on, and if you divide, you might find that those smaller units end up, being able to win over each other correctly, whereas the whole problem is too daunting. If you think of another problem, imagine you're a postmaster. This is a postmaster hat, and this is a postmaster mustache. You're a postmaster, and you have to deliver all the mail in America. Is a postmaster literally not a concept? Postman? To me, it's the head of the mail people. Whatever those. I don't know. Maybe it's a Canadian term. I don't even. Am I completely just postmaster general? Yeah. There you go.
Yeah.
That lady. We'll remove the mustache. Oops. Yeah. So there we go. You're the postmaster, and you have to deliver all the mail in America, in the US. And this is, by all accounts, like impossible. This is so hard. But if you think about delivering all the mail in your neighborhood, that doesn't seem so bad. You just get like some kid on a bike to do it. Now I have to draw a bike. You just get like some neighborhood kid to deliver all in the neighborhood. All mail. We're going with symbols this time. You're going to waste all this time drawing symbols. All mail in the neighborhood. So as a postmaster general, you realize that your problem seems impossible until you realize that you could divide your problem into many, many smaller problems, and you could go to the city itself, first the city, and then you might be able to go to each neighborhood, and each of those neighborhood. I gave the American spelling and the Canadian spelling just to make sure that we're covering all the countries here.
Represent.
Gotta represent.
Yeah.
That's mostly because I don't even know how to spell. But either way, you realize that this problem doesn't seem so bad. You have like, I don't know, 20 pieces of mail a day or something like that. It's a very small neighborhood. City might have like 100 pieces, and the postmaster might have 1,000 or whatever. And so, but the problem itself is kind of the same problem. You're still trying to just deliver mail to a individual person. to an individual person's house. The problem ends up sort of being the same, except house in this case is neighborhood, in this case is city, in this case we're at the top of the chain. So with this divide and conquer approach, we have basically broken down our impossible, daunting problem as to how we're going to deliver mail into all we have to ask is, okay, how do we deliver mail in the neighborhood? And then we just pass that up to the parent branch, whoever is in charge. How do we deliver mail to each? So in city, it's like, how do we deliver each, all the mail to each neighborhood? Neighborhood has to just figure out how to deliver to the house, and the postman has to deliver to just one city or each city. And so this ends up being a much simpler problem at each individual step. And we sort of basically all come down to this one final return statement, which this is kind of basically the base case. And as you can see with all the diagrams of these trees that we've been drawing, or these graphs, this is perfect for recursion. Because it essentially is, we take a way we solve a problem and we just apply it to smaller and smaller, basically, data sets. This is really cool. I want to save this. Cool. So with this in mind, there is a way that we could use the divide and conquer. Yeah, I'm going to put it on my own refrigerator. With this in mind, we can actually break down a sorting problem into smaller and smaller problems until they don't seem that hard at all to actually sort two numbers. For example, when it comes to sorting two numbers, it's pretty simple. All we have to do is just compare two numbers to each other. But let's take a look at a list of numbers, and I have a list prepared. Let's say we have 5, 9, 3, 7, 2, 8, 1, 6. Also, yeah, Joshua, yeah, good question, how we solve sorting. Ever since I've learned this, I have never, like every time I need to sort something, I always am doing it so slowly because I'm always, while sorting, analyzing how efficiently I'm sorting it. Feels like an XKCD comic in my head all the time, where I'm just like overthinking it. But I think that ultimately, if you think about it, you probably, when you're like sorting, you're probably still looking for the smallest number, placing it somewhere. You just do it too quickly to even think about it. I think some animals probably do BOGO sort, by the way. if you put a problem in front of a monkey, it probably might just keep solving stuff until it notices a pattern. But yeah, either way, maybe we can write a neural network someday that'll figure out a way to sort and we can see what it does. But okay. So if we take this problem, if we say we have to sort this array, we can implement an algorithm. In this case, it's called quicksort, which will use the divide and conquer method to essentially break this problem up into smaller and smaller pieces until sorting is pretty trivial, because all you have to do is just compare two numbers to each other. Or you might just end up with one number and you don't even have to sort at that point. And the way we do this is, the way we break up a problem is we have to choose a pivot. Let me move this down. We have to choose a pivot. Choose. And usually choosing a pivot can be as simple as taking the first number like we'll say choose a pivot index. And for simplicity's sake, right now we will just always choose always 0. Yeah. Pivot for the Friends fans in here. Basically, we'll always choose 0, which in our case is going to be the value 5. So this will be our pivot. Now at this step, what we want to do is construct 2 smaller arrays, a left and a right. And the left will be all numbers lower than 5, and the right will be all numbers greater. So in this case, we're going to end up with basically 3, 2, 1 in the left, in the order that they appear, and the right will end up with something like 9, 7, 8, 6. And now if we take a look at left and right, and we put them next to the pivot, what we get is 3, 2, 1, 5, kind of all on its own, not part of either left or right, 9, 7, 8, 6. So if we notice, we could kind of treat 5 as like our postmaster general. 5 is in the right place now, because all we now have to do is repeat this on this array and repeat the same thing on this array. But 5 will already be in the right spot. And so with our recursive step, or how many recursive steps would we have to do essentially on each kind of basically loop of each function call? This is a test to see if anyone's following along with whatever I'm going on about. Yes, thank you, Layla. You can always count on you. Great. We'll have to do 2 calls for sure, because we will basically do this whole thing on this array, and then we'll do it again on this array. But now the problem is a lot simpler, or at least it's a lot shorter of a problem. Basically, we want to choose a pivot again. We'll take 3 as the pivot. We'll, on the left of it, put a 1, and on the right of it, put or wait, no, I guess on both, right? We'll put 1 and 2 here, and 3 is in the right place. There's nothing on the right. So we won't actually end up recursing on the right in this case. And then here we'll recurse, we'll choose 1 as a pivot, 2 is fine. So we are already sorted. We won't end up, we'll recurse on each of these, but the base case, can anyone tell me what the base case will have to be? So every time we're passing an array down to through quicksort, we're passing a left and right array. Or sorry, that is, we're passing one individual array in. Yeah, awesome. The list size, if it's 1, so if we pass this 1 into our quicksort and we just have 1, we can just return it. Definitely. And once we return that 1, 2 returns here, 1 and 2 ends up returning here, 1, 2, 3 ends up returning here. So it'll be 1, 2, 3. And it'll be 5. And then some magic happened with this too, which totally made it a 6, 7, 8, 9 as well. And we have solved our problem by breaking things down at each step, and essentially not even doing really any comparing work, except when we're breaking down the problem. The base case ends up just being just a list of 1. And then we just have to send that back saying we have sorted this little array.
And because every time you pass a smaller and smaller array into the recursion, it's O of log n, right? Because it's getting smaller, right?
Yeah. Well,
or no?
it's not going to be just log n, but definitely we're going to have on average a log n case. But it's not going to be, sorry, log n is going to be part of our, of the order of this. But anyone have a guess for what is going to be, we'll say average case for performance of this? Just seeing if anyone but Joshua wants to take a guess before I reveal how right or wrong he is. But yeah, no, Josh was right. It will be on average log n. We'll discuss why average in a little bit. Let's maybe get to implementing it first. But if you think about it, on average, we're basically going to be comparing n operations on the first try, because we need to go and look at each number and figure out if it's going to be on the left and right. And then we're going to split the problem into two, but we're going to divide the input into two. So at each division, our n gets halved. So our problem becomes smaller at each step. So we're only going to end up calling log n operations, but we're still going to end up sort of doing n things per operation. Well, actually, is n log n slower than n squared? N squared is just n times n.
Yeah, it
So,
is faster because this n of log n is n times something smaller than n.
exactly. Yeah. So it's going to be n times log n. Yeah. So at each step, at first we'll do n things, then we'll do n half things, then we'll do n quarter things. So if you take a look, actually, and then we're gonna do n quarter things, and 8, for example, and so forth. If you think about it, the amount of operations per depth is still n. So this is n, this is n, this is still n if you add them all up. So each function will still do n, each like instance will still do n things, but the depth of this is most of the time going to be log n. So this is kind of, again, this is, I'm not going to lie, bringing me some nightmares of some advanced computer science classes, but essentially the reason why this ends up being n log n. Because instead of before, where we had to do n operations for bubble sort, and we had to do n operations n times, we now have to do a total of n operations log n times. So it ends up being quite faster. We basically reduce a lot of iterations that we didn't really need to do. Does this make sense, how we end up getting to n log n? Or should I maybe explain this a little bit better?
Yeah, once more if you can, please.
Yeah, okay, for sure. Okay, I'm gonna, does everyone sort of understand the gist of the algorithm? If you don't yet, don't worry, because we're actually gonna code it up in a few minutes. So we'll kind of go over it basically one more time. But I could do a quick little explanation of the algorithm one more time if we want to do that. Okay. So once again, uh, being a divide and conquer algorithm, uh, let's say we start again with quicksort right here. So we have 5, 9, 3, 7, 2, 8, 1, 6. The whole point is for us to divide the problem into smaller chunks and then be able to figure out how to sort that. So we're actually going to end up dividing the array in halves at each step. And eventually, the array is just going to be of size 1 at some point. And at that size 1, we basically say we're done. There is nothing to divide. We can essentially, we're done our divide and conquer. We have finished conquering, essentially. So the dividing would be the step where we actually split it. Conquering would be where we recurse and split again. So the conquering in a divide and conquer algorithm is in when we make the recursive call itself. So we'll say this is the divide. Whoops. We'll say this is the, oh, come on. Okay. I don't know if all of my struggles are totally visible in Zoom. Cool. This part is the divide part. So we divide by choosing a pivot index. At this point, we'll just go with index 0, so its value is 5. And then we create a left. This is all lower values. And this is all higher values. So just quickly, what's the what's the order of magnitude of just the divide step itself, given n things? Yeah, exactly, it's n. Oh, also about good questions, and you say, do we combine at the end? We basically do, and I'll try to elaborate on this more. This is probably the hardest part to think about with recursion, is how does everything sort of come back together? And I'll go over that in a little bit. I think it'll be more clear in the code how everything sort of ends up returning an actual complete array. But yeah, no, I totally understand the confusion. It's something that I think is one of the most tricky parts of learning recursion is you get to the base case, but okay, so what, right? So the divide, yeah, Layla's already got the answer. So this divide step is going to take O of n, right? Because we're just going to basically start at a pivot, and we're just going to go through every number, and we're going to ask, is it higher or lower? And if it's higher or lower, we're going to put it in the left or right column respectively, or unrespectively, I guess. So once we've divided the problem, we want to conquer it. And so the conquer step in divide and conquer is usually where we end up calling our recursion. So in this case, we're going to end up calling quicksort left and quicksort right. And so, by the way, Bao, maybe this will make sense right now, because we can call this sorted L. So we can say that whatever quicksort at this point will return to us will be sorted L. This will be sorted R. And the final return of the function will be sorted L
plus R.
Plus pivot, because we don't want to forget the pivot, plus sorted R. So basically, if that makes sense, to kind of answer how we combine in the end, we do. We basically take the outputs of each and we'll end up kind of combining them, right? So quicksort will run through this. It will now receive 3, 2, 1 in it. It will divide based on some pivot, either 3 or 2 or 1, whatever. It'll divide it again. It'll conquer on its own, excuse me. It'll return its own sorted versions of its smaller problem until we reach our base case where the sort doesn't have to divide at all. We just return the number itself.
can you please go through the left portion like 3, 2, 1, how we will, suppose we chose 3 as the pivot. So 2 and 1 are remaining. So can you go further with that? Like how we
Yeah,
will,
sure.
yeah.
So let's say we say pivot equals 3. What does left equal now? Now we're doing a divide, what will left equal?
So we are not comparing. So anything will be less than 3 will be all in the left.
Mm-hmm.
So it will be both 1 and 2, but it will be not sorted one, right?
Yeah, it'll be 2, 1 because we're pretty much just going to go through and look at 2, get in there, 1, get in there, right? And right is actually going to end up being empty in our case.
Yes.
So we can pretty much we can actually put right into quicksort, and quicksort will see that it's an empty array and just return the empty array right away, which means that this instance of the function will get sorted L it'll return 1, 2 because we'll trust that the recursive call to 1, 2 to 2, 1 will sort it correctly. Sorted right will just be an empty array, and then we'll combine it. We'll give that up to the parent instance that called it, which is right here, and so that's going to end up being 1, 2 plus the pivot, and so that's going to be sorted. So each call will sort what it's got and give that value back to the parent, right? And when we get that back to the parent, we know that for sure that small chunk was sorted correctly. So all we have to do is combine it. So all of the child functions will sort what they have, pass it up to the parent. The parent, all will do will just add them together, pass that up to the parent. That'll add each of its halves together and keep passing that up until we're done with the function and we've finished the whole chain. And again, I think we'll get into code. I think we should probably just get into the code, I think, and try to actually code this up, because I think that might help explain some of the lingering questions. Okay, let me just close this for now. Oh yeah, good idea. Actually, you're right. We've been going pretty hard. How about let's do a 5-minute break, and we'll be back at what is West Coast time? 8. Would it be 8? Yes, 8:30. Cool. So I'll put up a timer real quick. We can take a 5-minute break. If anyone has any questions during the break, I'm also still here. We can go over anything else. So Joshua, you asked about radix sort and bucket sort. Oh man, it's been a while since I've looked at radix sort. But I think there's kind of basically a similar thing. Right. Essentially, both radix sort and bucket sort try to take a look at the actual input that you're given and try to figure out a way to sort without comparing each element. They're just trying to find kind of hacks within the input that you're given to know how to sort, how to end up with the complete sort. I'll go over bucket sort because I know that one a little bit better than radix sort. But basically, you know, you have something like you have something like 2, 5, 0, 1. You want to sort this. You first want to find the largest number in the array. So find largest, which will be 5, and create array. Yeah, no, I know what your question is. I just wanted to make sure that for anyone listening that they understand what we're going to end up doing, right? Create array of size 5, and basically set them all to 0. And then as you go through the array, go through original array. It's kind of like count sort. I'm pretty sure it's basically the same principle as count sort. And every time you see like 2, you basically add 1 in bucket array. I'm going really quick with the explanation here. Add 1 in bucket array to that specific index. So this is the indexes. This is 0, 1, 2, 3, 4. I guess we should have 5 in there as well. So size 6 technically. So it'll be 5 plus 1. Basically, we see a 2, we add 1 to it. We see a 5, we add 1. We see a 0, we add 1. And we see a 1, we add 1. And so basically, once we're done this, we can just go through this array and see, okay, well, there's 1, 0. So append 0 1 times to the result. So this is the result. Append 1 once, append 2 once. Don't do anything with 3, skip that. Don't do anything with 4, skip that, and append 5 once. And so basically we will have like a sorted result. So, oh, we're almost done. But essentially, think about how many times we're going to end up running through this array. What's the number that we're going to end up running through that array? What's the like worst case? Or what is it dependent on? The size of this array that we've created for buckets. Basically, to answer it quick, the size of this array is going to be based on the maximum number. So you're right, everything about this is linear. Every single step is linear. But if this number is huge, then you know, this number just has to be like larger than n squared, for example, for it not to be worth it anymore. So even 5 makes this or I guess what number would, if this is 4 squared, that's 16. Literally having 17 in here would no longer make this sort worth it because it's slower. So it's linear, but it's linear on the maximum number. And so you're better off writing bubble sort in this case because it's still gonna do 17 steps instead of 16 like it would for bubble sort. That's kind of how they compare, and that's probably why you don't really see these sorts used often. O of nk, so k is probably going to be in radix. I forget what the k is. It's probably like the order of magnitude or something on the number. I mean, once again, it's the same argument. If k is huge, like it looks like it's linear, but if k is very big and n is small, then you're still better off using something like n squared in practice. So when you look at something like O of nk, it literally is just n times k. It's a linear based on two variables, based on the size of the input and the like largest number or whatever k is in radix. But essentially that might scale in practice very horribly with real data. I can explain to you more later. I've already went on a bit of a tangent. Okay. Hey guys. All right, welcome back. So let's actually go ahead and code up an example of quicksort, and we can go over the code that we've created essentially. So again, we're going to want every time we're gonna do a recursive approach. So once again, can someone remind me the two mandatory steps in a recursive function?
Base class first, and the way to reach the base class.
Yeah, we want a base case and we want the recursive case. So to reach base. Cool. So in our case, so I also wanted to go over, we can actually solve quicksort. We can either do the thing where we create left and right, or we can also solve it by having an in-place algorithm. So in-place being that we don't actually create any new items in memory. We can just use what we have and just modify the array in place. So we can try to take a look at that approach. And I don't think it's going to be necessarily too much more confusing. But essentially, when we think of left and right, when we think of those two arrays, instead of creating out of the case that we had before, where was it? Out of this example, where we had 5, 9, 3, 7, 2, 8, 1, 6. When we had like this array and we chose 5 as the pivot, instead of figuring out, like low and high will start at 0 and 1, 2, 3, 4, 5, 6, 7, 8, 8 respectively. And what we could do is when we're trying to figure out the new array, what we could do is we can actually, as we go through each element, move the element over to either the left or right of the pivot, and then pass to the recursive step the beginning and ending of the left array and the beginning and the ending of the right array. So after one step, what we'll end up with is basically 3, 7, 2, 5, 9, 8, 1, 6. We're basically in place modified the array, where the low for the left will start at 0 and end at 2, 2 being the index. So, and then this one will start at 4 and end at 4, 5, 6, 7, and end at 7. And this way, we don't have to end up creating any more memory, so that our recursive step, which already is going to take up quite a bit of memory, will not have to then essentially exponentially increase that memory, which we potentially might even get Python really upset at us if we do that. So with that in mind, I'll keep the notes here. The base case in our case will then be if low equals high. basically. That means that we have either reached a case where we only have one element and the array is of size 1, and so low and high start and end at the same place. Or we might actually end up with an array of empty, as we've seen in some cases where we can pass an empty array in. So we want to, that will make low actually be higher than high. I also noticed that I wrote 7 here for some reason and 1 in the other case. 3. This would be 3, 2, 1 after 1 step. And this would be 7. Okay. Sure. Almost. Cool. And in that case, we can just pretty much return. So if you guys remember the first week, books is going to be an array. And since we're passing books around as a input to a function, it gets passed by reference. So when we make modifications to books, we pretty much don't even need to return books or do anything to it. It will be modified somewhere, wherever it lives in memory. And that actually works for recursion as well. So wherever books exists in memory, whatever it is we do to it will be modified in place. We can return books here as well anyways, but essentially we don't even have to do anything. We just pretty much need to return. So now, in this case, we need to start doing our divide part of the divide and conquer. And so for the divide part of this algorithm, we want to choose a pivot and break the problem down into 2 smaller problems of a left and a right array. So first, we want to look in the range of low and high. This is essentially looking at what our kind of virtual array is, right? So in this case, at the beginning, it's going to be 0 to 8. It's going to be the whole array. In the next step, it might be 0 to 2 or 4 to 7. Basically, we want to just look through those numbers and swap swap just that instance of those numbers around. So if books I is genre is lower, oh right, we haven't chosen the pivot yet. Let's choose a pivot. And let's always just end up going with whatever is the first number. If it's smaller than the pivot genre, then we want to take the number and move it on to the left of the pivot. And we're going to do that in 2 steps. We're going to first take that lower number and we're going to move it just to the right of that number. We're going to make a swap between those 2 places. And then we are going to take the 2 numbers that are right next to each other, the pivot and that number, and just swap them. So we're going to basically do a double swap. So first, move books at I, next to the right of pivot. So whenever we want to swap 2 elements in an array, first thing we want to do is save the first element that we are going to be moving. So we're going to be moving books at, well, actually, you know what? Sorry, pivot is going to be a pivot index. It's going to be easier for us to deal with it that way. And so books at pivot index dot genre. So pivot index +1. So we want to move it to the right of pivot index. We're going to say books at pivot index equals books at I. So at this step, whatever was that book that had a genre that started in the alphabet earlier then the current pivot, or in this case, for example, if we saw like the number 3, for example, we would first move it all the way over next to 5. And then whatever was in that value, which was 9, since we overwrote that, we will replace where it was that we we just overwrote it with the temp value. So books at I equals temp. Cool. Any questions so far about this first swap that we did? So in this case, now that we have swapped this value, to actually put it to the left of it, we would want to do a second swap. It's going to look pretty much exactly the same. We want to swap pivot with element on the right. And the reason we're doing it this way, because if we were to just say move this element all the way to the beginning instead, we would then have to shift a lot of values around. And here instead, we pretty much just have to shift, move it close to the pivot and then flip it. And so pivot sort of moves down the array. And so eventually pivot is going to end up hopefully somewhere in the middle once all of this for loop is done. And so once again, we want to store the current value that we're going to be replacing. We're going to now overwrite it, equals books at pivot index +1. So now it's the element that we're now interested in. And replace the thing we just overwrote, pivot index +1 is temp. And so now we want to move up pivot index +1 because plus equals 1, because now the pivot index has been shifted over. So if we were to think of what we just did, if we were looking at the number 3, we first replaced it with 9, and then we replaced 5 and 3, so it would be 3, 5, 9. And with that, we have to update the pivot index to move over 1 value. Cool. So at this point, when all is done at line 43, we should end up with an array that looks essentially kind of like this modified array. All of the values that matched this if statement would have been moved over to the left of the pivot, and all of the values that didn't match the index would have just kind of stayed where they were or might have gotten swapped, but they essentially would end up being on the right of the pivot because our pivot was always the first index. So any questions about this? There isn't really an easier way to swap two values without having to at least write 3 lines. 3 lines is the shortest that you could swap 2 values with. Essentially, at any moment, you're going to end up overwriting one value with the other. We possibly could have done this simpler if we didn't try to do an in-place algorithm. If we wanted to do like actually creating a left and right array, that could have been simpler, but we would have ended up having to create a lot of memory usage. So the only way we could do something in memory like this, where all we're doing is just modifying what we're given, pretty much there isn't a faster way. A, B equals B Does it in Python? Like you can just do something like that? I mean, maybe there's some funky Python way to do it. This
In
would
JavaScript it
essentially
works.
be,
In
sorry?
JavaScript it works, yeah. I don't know about Python.
Yeah, I don't know. I guess I can look into that. I think in general though, if we were trying to be like just language agnostic, if you think about what it takes to swap a few numbers around, um, like if we are trying to say we're trying to swap 5, 9, 3, if we want to move 3 over, at first temp, and this is let's say this is the pivot. So temp, this will be 9. Books pivot +1 equals books I. We're now basically replacing this pivot index with 3. So this is kind of why we have to remember what temp was to begin with. Once we've replaced this, we want to remember where it was that we replaced that value from and replace it back with temp. So I mean, logically, that there will always be, even if what Layla says works. I don't know if anyone knows how to write that in Python. We could definitely add that in. I'm not sure. I mean, there also, in the end, whatever process does the swap will always have to kind of store a little bit in the temporary variable and then replace it. So I guess this is like the language agnostic way. If there's a Pythonic way, we could definitely add something like that.
I mean, even if that syntax does work, under the covers, A, B equals B is doing internally this sort of temporary swap holding thing. And then your code is just more explicitly sort of what's happening, right?
Right, exactly. So in the end, if we're trying to swap some things, imagine even if you just had 3 things like you literally have like a box of 3 apples or something and you're trying to swap them, you have to pick up one into your hand and move the other one around and kind of place it back. That temp is sort of us picking the number up into our hand. Like there's always going to be kind of like a 3-step process of picking up, moving, and putting back down. Cool. So now we have, does anyone have any questions about the resulting array and how it is that we have like a left and a right, and how we can get a left and a right now?
That's pretty cool. What
That is
Josh
pretty cool.
put in the channel, and that's easy to read too.
That is pretty cool.
Yeah, it's nice and elegant, huh?
Yeah. Okay, cool. So if that's, we can, I mean, I could add that in. And if that probably is a little easier to read for everyone. So let's do something like that. If I've never actually seen this before, so that's pretty cool. Still credit goes to Layla though, because she wrote the first thing. What is this going to end up being then? Pivot index +1 and our yeah, I don't know if it's Pepe. You know what? Let's get back to that maybe in the cleanup potentially, because I know that this works because I had to write it earlier. But essentially, now that we've swapped it, we now have this array that we can basically break down into a left and a right and start doing the conquer step. So to conquer now, we're going to have to call quicksort twice, essentially. One for the left and one for the right. So we can go ahead and do quicksort on books, again, passing in this modified array. But the low, what would the low value be for the left-hand side? it would still just be low. It would be, in our case, in the very first step, it would be just 0, or it would be the low variable. And what about the high variable? So the variable that we're going to be reading up to for our kind of virtual left array.
Favorite index.
Exactly. Right. So we're now going to be doing quicksort once again, but we're only going to start at low, and we're only going to go up to pivot index instead. So the high value in the second call is not going to be 8 anymore. It's just going to be 2. And so we're not going to, we're only going to analyze the numbers 3, 2, 1 and do this whole reshuffling one more time. And then for the right-hand side, we are going to do the same, but our low value is going to be, anyone before I finish typing it? Okay, +1. Right, so we're going to start at the index after the pivot, and we're going to conclude at the original high value. And because we're doing this all in place, we're now quicksort A, instead of, let me erase this and annotate some more. Now, when quicksort calls on the left-hand side, it's essentially just going to reshuffle the values 3, 2, 1. It's going to leave 5 alone. It's not even going to get to that because this value is only going to go up to 2. So it's only going to reshuffle this part, whereas the second part will only reshuffle the values after 5. And so it's only going to reshuffle these values. And it's going to leave 5 alone because we're not including that in there. And because it's in place, and because books is passed by reference, this array, wherever it lives in memory in Python, is just going to be modified kind of like a pointer. It's just going to be modified because it just exists as some kind of box that all of these variables point to whenever they are modifying books. So once this function is called, our books should be reshuffled and resorted into the correct positions. And that is pretty much all there is to say about this version of the algorithm. And I think all we have left to do is run it, and fingers crossed I didn't mess it up too much. But does anyone have questions so far? So here we want to choose our pivot. Bao, that's a good question. We'll get to that after. At line 31, so at line 31, this is where we choose the pivot for the current given array that we're analyzing, and we're always just going to choose the first element in our case. There's actually lots of literature on what is the best pivot to end up choosing, and we can quickly discuss that if we hopefully have enough time. Looks like I'm going to be keeping you guys up a little bit later again. Apologize. But the first line is us choosing a pivot to which from which we sort our lefts and rights. Yeah. Cool. So let's actually run this real quick and see that it all does work. So once again, if we recall from last class, I had this books data kind of CSV that basically had a bunch of different data. And I have 3 versions. I have a short, a medium, and a long array of books. Last time we implemented a insertion sort, and I think it would be fun to compare the two now to see if we've gained any sort of performance. I also created this quick little function that double checks whether or not things are sorted, just to make sure that we have actually written our algorithm correctly, because last time we pretty much just tested runtime, didn't really check whether or not things were sorted. Whoops. So let's try out. Okay, so this was the quick version, or just 10 books version for insertion sort. No, what did I mess up? Oh, thank you. Cool. So it was not sorted to begin with, sorted afterwards, and it took us 0.15 seconds, so, or 0.015 milliseconds, so super quick. But that makes sense because it was only 10 books to try out. Let's try out our new quick sort. So over here I have quick sort calling. I have books, this variable books to sort, and I go from 0 at the beginning to the length of the books to sort. Let's try this out. Okay, so it actually ended up being a little bit slower for 10 books. So that's interesting. I bet if we keep trying though, it'll give us different values all the time, but it actually ends up looking a little bit slower. Fair enough though, potentially spinning up recursion instances will take a little bit of time to spin up each function, and potentially we might be causing a little bit of a delay there. Let's actually see if we've just wasted our time though. So let's test with 1,000 books. So once again, here's the insertion sort for 1,000. And that took 89 milliseconds. And fingers crossed, this wasn't a colossal waste of time. We should see at least a little improvement here with 1,000 books. And yeah, in fact, we do. We see almost a 10 times improvement. Yeah, it's wild, right? Just with, I mean, and it is exactly a magnitude. And I mean, that makes sense because clearly we are no longer doing an n squared solution for this. There is one problem that we have with this, and it's actually something to do with the fact that we're using recursion to begin with. If we choose 2,000 plus books, that means that we are going to have to create 2,000, basically 2,000 recursive calls. And we're going to run into a bit of a pickle. So first of all, this is the insertion sort. It's going to take us about half a second. But if we do the same code for quick sort, 0, I have to rewrite this real quick. Because we're going to run so many instances of it. Wait, hold on. That was less climactic than I had hoped. Why did that work? It shouldn't have worked. I'm wondering if I messed something up. I'm not fully sure Yeah, this definitely wasn't working for me before. What was supposed to happen was Python was supposed to tell us that it's run out of memory, essentially, or we've reached the limit of how many recursive calls we're allowed to make. But for some reason, magically, it works this time. Definitely wasn't working before class. We still won't actually have time to create a solution, but essentially we would actually have to end up creating a iterative approach to the solution, which would still end up having the same algorithm where we still divide and conquer. We just end up using our own array of memory to keep things in order, but we won't have time to implement that now. But essentially, it's possible when we write too many recursive calls, we are going to end up running out of how many functions you're allowed to call over and over. And in Python, the standard is 998, which is why my book's medium is actually set specifically to that. Because any longer, let's see, any longer should break this. I think I might have some variables messed up somewhere. I don't know what's going on. I'll have to look into this later. My bad. But okay, let's just go back to talking about quicksort for now, the way it is. No, my quicksort B is not even defined right here. It's just returns books for now. No, I think, yeah, I think that my point, I wish I could have demonstrated it a little bit to nail it, but essentially, you can't. There will be limits to how much we could recurse, and that is an unfortunate reality of recursion. And so sometimes what we're going to have to end up doing is figuring out ways to reduce the amount of recursive calls we have to make. And things like that we're going to end up talking about next week. But first of all, I would like to sort of, before we end the lecture, I do want to kind of go over why is quicksort that much more efficient. And so we've already figured out that in some cases, in most cases, the big O is going to be n log n. And the reason for that, I'd like to kind of go over one more time, is there are two steps to the problem, right? The first step is to do the divide. And the divide just means go through every index and so like literally right here, this is O of n, right, at each sort of step. However, most of the time, what we're doing to this n is, I wish it would scroll with there we go. You can see all the code now. Basically, at each step of the function, we are going to be running this for loop where we're going to be looking at every single element of our array. So this is going to be O of size of array. But what do we do with the size of the array every time we call quicksort again? Basically in most cases, we kind of get to a point where we pretty much half the size. So we can pretty much, let's say in the best case scenario, we always end up halving the size every time we call it. So every single time we call a new instance of quicksort with a smaller and smaller version, we're in best case always going to end up halving the array over and over.
We just keep giving it less and less to do.
Yeah,
We're
exactly.
reversing what we're calling on it to do less and less and less and less and less.
Yeah, absolutely, exactly. And if we think about it again with the tree of doom of recursion, the first call to quicksort will run n times, right? And then it will, in best case scenario, call 2 more versions, but then the operations in there have to just run n divided by 2 times each. Oliver, what do you mean we're approaching asking you to do the pivot sort 0 times? Yeah, I mean, if we could, actually, I think I get what you're getting at, and I think we're gonna we're gonna quickly finish talking about this and discover a quick flaw in quicksort and why we don't want to use it, and that might end up answering Bao's answer as to what is better, merge sort or this one. But at this point, we have now called one instance, which called 2, which again will call then 4 instances, and it'll go n divided by 4, n divided by 4. And if you think about it, if you see what's going on at each like depth of calls, we still only end up looking at n elements. So we still end up analyzing n elements at each sort of depth. When we recurse and we go to the next depth of our recursion, in total, we're doing less at each step, and in total, we're still looking at n that many times. But because we're halving the problem every time, and we're going to end up at our base case much, much faster, in fact, log n times instead of n, we end up only having to do this sort of this depth new recursive step only log n times. Because as we looked before, anytime we are halving the array, that ends up becoming a log of n operation. And so we're only going to end up doing log n steps, where at each of the steps, we're going to end up doing n operations. So we have n operations at each step, and we're going to multiply that by log n steps. How many people have I lost? Because this is, and don't worry if this is confusing. It is pretty kind of tricky to wrap your head around, because you kind of have to think about this function doing n things, and then it's done, and it does. Then it's these functions' turn to go and look at n, and then it's these 4 functions' turn to look at n, and then it's these functions to turn to look at n. And so we kind of keep looking at smaller and smaller subsets, but we're looking at them basically the same amount of times. It just so happens that we don't have to keep splitting we don't have to go and do this split that many times. We only have to go down log n times. So if n is 8, we're only going to end up recursing 3 times until we reach a array that hits our base case and does nothing, does an O of 1 operation.
And they all individually add up to n anyway, so it's not like they're adding. Yeah.
Yeah. If there was a way for us to do less things here, yeah, then we might even find a more effective thing. Which I don't know. I mean, my algorithm computer science professor once held the record for like 2 years for having the quickest sorting algorithm out there, and it was something like n to the 0.75 log of like 2, 3. I don't know. It was like a very, very specific thing. There's micro adjustments we can make with all algorithms, which was kind of just kind of funny to know that there's people that basically just gain PhDs by knocking down like a tiny little number on their sorting algorithms. But yeah, essentially that's how we end up at this n log n. This n represents how many operations we're doing per step, and this log n represents how many steps we end up doing. So how much depth we kind of go down. If we were to be more pedantic or something, we could say that these all are steps, and we would end up kind of adding them all up anyways, and they all end up amassing to n steps per depth. But okay, we're super over time so far. So I just wanted to ask one question. What do you think is, how I want to say this in a theatrical way, but there is a catch with quicksort. And there is actually an input that will yield a n squared result. Does anyone know what the input might be?
Well, didn't you say something like 990? I mean, there's an input amount that causes the recursion to exceed its memory requirements.
Yeah, that's a bit of a different problem, because that's like an actual practical problem with computers, whereas we're thinking theoretically, what is, in general, what is an input that will yield an n squared result?
Oh, okay.
And in fact, we can run it, and we'll see that in one case, quicksort actually isn't that great at all. In fact, it's like strictly worse than insertion sort even. And I won't hold you guys too much longer. Essentially, if the array is sorted already, quicksort is going to end up being n squared. And if you think about it,
it's doing all that work regardless. It's right.
Exactly. It's still generating the left. It's just that it will always generate, because we're choosing a pivot at the beginning, we're always, and it's already sorted. So let's say we take something like 0, 1, 2, 3, 4, 5. We're going to take, or it's sorted backwards, I guess, is technically the worst. No, never mind. It's sorted the right way. Yeah. If we take pivot 0, it's going to go and loop through the whole thing and create a right array with everything in it. And then it's going to basically create a right array of this size. Then it's going to go through that. It's going to create a right array of this size. It's going to go through that and keep going and going and going. And that ends up just being n squared with extra steps, where we pretty much go through a whole recursive, we add overhead because we're doing a recursive step. And quicksort ends up becoming not very efficient in that case. We can actually see it because if I call, let's say I call the insertion sort first, and then just pass in sorted books in, and we see the performance in that case. Oh, well, now I get the maximum depth exceeded. Great.
Dude, it's not your night, huh?
It is not my night. I think maybe I wasn't saving right or something. Okay, there we go. As you can see, because the array was sorted before, quicksort took as much or even really longer than insertion sort, because there is a little bit of an overhead when it comes to creating a recursive call that basically insertion sort does not have to deal with. So quicksort doesn't really have all of the answers. And in fact, in your assignment for part 2, you will be writing a merge sort, which has generally a better time with these cases. But even if we instead chose a random pivot instead of always choosing the first pivot, our problems most likely would end up going away, because if we choose a random pivot, we're more likely to end up breaking the problem down into more fair chunks and end up having smaller work to do per recursive step, and thus having less recursive steps overall.
Because it breaks it down into smaller chunks that are already in order, so they're just not doing much.
Yeah, but even still, the reason it becomes n squared is because we're still going to end up doing n operations n times, because we're going to end up doing a depth of n instead of log n, because we're no longer breaking our list, our input, into halves. The ideal would be if we really just find a pure half to break down on, and that will get us down to our recursive step the fastest. We'll have the lowest amount of depth of our tree of recursiveness. But when we only break down our problem, when we can't really divide it effectively, divide and conquer ends up being almost no better than just an iterative algorithm. And so I will end it here, I think. We pretty much got to almost everything that I wanted to talk about. One thing that I think is fun to discuss real quick is actually in practice, we might notice that insertion sort or even other sorts might actually work better for certain types of data. So as we've sort of talked about bubbles or bucket sort and things like that, where some sorts might be more efficient with smaller data or more efficient with large pieces of data. So in practice, what we end up doing often when writing effective sorting algorithms is we end up combining them. So we can actually combine insertion sort and quick sort to be effective, where we use quick sort on very large data sets, but insertion sort on small data sets. Like we saw with the test of 10 books, insertion sort was actually quite significantly better on just 10 books. So it's possible, and actually the Python sort called timsort actually uses a combination of merge sort and this other fancy sorting algorithm that the creator of Python, or a very big contributor of Python, his name was Tim. I looked up the Wikipedia article before. Essentially, that uses a combination of a n squared sort for small data and merge sort for large data. So with that fun fact over, for your assignment for the week, for the second part, we're now going to implement a merge sort and that's going to follow a pretty similar pattern as quicksort does. And it's going to, again, use a divide and conquer approach to create a more efficient algorithm that we can then use for maybe larger data sets. Whew. And if it's tough, the hardest part, I think, with recursion is trying to debug it, because keeping in mind that sort of recursive tree structure is always quite a challenge. So definitely put in a lot of console statements. I sometimes even put in a counter, count equals 0, for example, and every time I iterate, I do count plus 1 to remind myself what depth I'm at in the recursion. So sometimes that helps me be able to figure out, oh, okay, we're at depth 3. The algorithm should have been 3 times smaller now, but it's not 3 times smaller, for example. So a little tip on that. Okay, so it's 20 minutes past. I apologize once again. Any last questions before we end for the night? Yeah. Whew. Yeah. All of us East Coasters are probably feeling it by this point. Cool. Best of luck to everyone on the assignment. Let me know, and I think if let your team leads know how you find the assignment and the challenge and everything, and maybe we can discuss briefly next week if there's any more remaining questions on recursive algorithms and things like that before we dive into more algorithms. So that's always something to look forward to. Cool. Have a good night, everyone, and I'll see you next week.